Hello, this next video in a playlist that I'm calling General Linear Models Design of Experiments, and this is part 9 of an 11-part mini-series in hierarchical designs. Here we're going to look at a nested and crossed design. Now, as to illustrate, there's three factors A, B, and C, and A and B are crossed and factors B and C are nested. And so this would be the design. So we have factor A, 1, 2, and 3. Factor B, there's 2 levels. And so each of these are crossed. So 1 and 1 are crossed, 1 and 2 are crossed. So that's like a factorial design. So each level is crossed with the respective level of B. But factor C is called nested. So it is nested within factor B. So these 1, 2, and 1, 2 are not the same. It could be just called 1, 2, 3, 4. But traditionally they call it 1, 2, 1, 2, even though it doesn't have to be. And these are nested within B, but there also can be, crossed with factor A, but within B. And I'll show you that in a second. So this is sort of the setup. Now the models are this. So the Y, I, J, K, L, so factor A, B, C, and then that's the number of replicates. Oh, and in this there's 2 replicates within each setting. So it's the grand mean plus factor A effect, factor B effect, the interaction between A and B, factor C, but within factor B, and then the interaction of factor A and factor C, but it's sort of nestled within factor B. That's what this represents. And then the error terms are considered sort of nested within all 3, and then that's the replicates. So in this example, A is 3, B is 2, K or C I should say, C is 2, but we use the index K, that's what that means. And then L goes to 2 because there's 2 replicates. Error term normally distributed, mean 0, constant variance sigma squared, independent from each other. In matrix form, we'd write it like this: y is equal to x star beta star plus epsilon. So it is a linear model, but then we partition it into each, the different effects. So we have the grand mean, factor A, factor B, the interaction between A and B, the factor C, but it's nested within factor B, and we have the interaction between A and C, but as a reminder, this is sort of nested within factor B. And then we have an error term, and the error term is multivariate normal, mean vector 0, covariance matrix sigma squared I. Now this is all very informative, but when I was first learning ANOVA designs, for some reason I had to see the design matrix before I finally understood what was going on. And so that's what that's actually why I always provide the design matrix, because it was so helpful to me many years ago. And so this is it. So we have the y vector, and it's, sort of indexed by factor A, B, C, and then rep. And it goes all the way down. So the first column in the design matrix is all 1s, and that's associated with the grand mean right here. Now, there's 3 levels in factor A, so we're going to have alpha 1, 2, and 3. So we, when we do this multiplication, we have to pick them off one at a time. So the first column is 1s, while we're in level 1. So all these, the first index is a 1, and here the first index is a 2. So we move over a column, and that's all 1s. And wherever there's not a 1, it's 0s. And then we're in level 3 within factor A, and that's what this is. And that is, so when we do this multiplication, we pick off the right parameter. Now there's 2 levels in factor B, so we need beta 1 and beta 2. And since it changes faster than A, then there's going to be repeat columns. So this is level 1 of factor B, level 2, and then it repeats. So this is level 1, level 2, level 1, level 2. And then the interaction term, they get their own parameter. So there's 1, 2, 3, 4, 5, 6 because it's 3 times 2. So each one receives its own effect, its own parameter. So there's 1, 2, 3, 4, 5, 6 columns for that interaction space. Now, so factor C, which we're going to call gamma, but nested within B, they get, so this is B, and there are 2 levels, so they each will, there's 2 levels within each, but since it's nested, they get their own effect. So this is B, so we get 1, 2, and then this can be thought of as 1, 2, but since it's nested, it's really 1, 2, 3, 4. And that's why it gets 1, 2, 3, 4. They get 4 parameters. And then it repeats. So then here within level 2 of factor A, and then B, these are nested within B. So so this is 1, 2, 3, 4, the 4 effects within these. And then it repeats for when level 3 of factor A. And so they're nested within B, so they each will get their own effect. They're nested. Now the interaction between factor A and factor C nested within B, since they're nested, they will get their own effect. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 parameters associated with this. And so there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 columns within this interaction space nested within B. And since it's nested, it means that it gets its own effect, its own parameter. And that's it. So anyway, for me, I just find these design matrices so informative of what these models are actually saying. Okay, so if it helps you, that's why I do it. Now the column spaces of the design matrix looks like this. So the column space, the first column of ones, is actually a subset of the column space of alpha and the column space of X beta. Now, both of these are subsets of the interaction space, and column B, of course, is a subset of factor C, so X gamma, because it's nested within B, then this is a subspace of this. And then both of these are subspaces of factors, the interaction between A and C, but nested within B. And so, since everything here is actually a subspace of this column space, the perpendicular projection matrix on the whole column space, which we usually denote by M, is actually going to equal the perpendicular projection matrix onto this subspace, because they're equal, and perpendicular projection matrices are unique, so they have to equal. And so a kind of a brief little heuristic argument in the development of the structure of these perpendicular projection matrices onto these little subspaces. So from previous designs, we've looked at the grand mean, alpha, beta, and the interaction space. And then we set up little subspaces where all of these are orthogonal. And I would look at the two-factor factorial design with interactions for a big development of this. Now these are all pairwise orthogonal. So then the perpendicular projection matrix onto this space, since this is a subset of that, we can take the perpendicular projection matrix onto these, and we take this one minus that, and that's how we get this one. So this is J, and this is M, or M alpha minus J, and the perpendicular projection matrix onto this was M beta minus J, and you just add those up and you get this. Now to look at this column space here, one is a subset of X beta, and X beta is a subset of X gamma within beta. We can create little orthogonal column spaces. And then the perpendicular projection matrix onto this, remember, yeah, the perpendicular projection matrix onto X beta orthogonal to 1 is M beta minus J. But here we're trying to find the perpendicular projection matrix onto this orthogonal to that. So it's actually the perpendicular projection matrix onto this column space minus this perpendicular projection matrix, which is this. But this just boils down to M beta. So that's the perpendicular projection matrix. And the reason we're doing this is it's going to help us when we partition the total sums of squares. So now for the whole column space, everything below it is a subset of this interaction space between factors A and C nested within B. So it's alpha, gamma nested within B. And so we create a little subspace. We make, we carry these over, which we've created up here, and then we create, then we make we have to get rid of some columns, but then what's left is orthogonal to this, and they span the same thing. And that's the important part. But then all of these subspaces are orthogonal. So we can take the perpendicular projection matrices onto each of those and add them, and then that's the perpendicular projection matrix onto that whole column space. So the perpendicular projection matrix onto this subspace is the perpendicular projection matrix onto alpha, gamma within beta, and then subtracting off everything below the perpendicular projection matrix. And then that boils down to this. Now, since the column space of X star, the full design matrix, is actually equal to the column space of this interaction space, then those two perpendicular projection matrices have to equal. So M, which is the perpendicular projection matrix on the X star, is actually this perpendicular projection. And how to find that is you add all of these perpendicular projection matrices and you get this. Now what we do is we want to partition the total sums of squares. So what we have is orthogonal subspaces here, and then we can just, and then M is defined as the addition of each of those perpendicular projection matrices. So when you partition the sum of squares total, then you add and subtract 0, so you add M and subtract M, and you create these. Well, I minus M is always the sum of squares for error, but M can be broken down into J, but that's reduced, it's eliminated by minus J, and then M alpha minus J, that's this one, and then M beta minus J, that's the perpendicular projection matrix onto this one. This one is this perpendicular projection matrix. That is this one. And then this is this. And then of course we have the sum of squares for error. Well, that's it. So that's the sum of squares for factor A, sum of squares for factor B, the interaction sum of squares. This is the sum of squares for factor C nested within B. This is the interaction between A and C nested within B, and that's the sum of squares there. And to me, that's just so mind-boggling when we're going to illustrate this design in our software. So when we calculate these crazy matrix multiplications, it's going to equal exactly what R puts out. And anyway, I just find that so fascinating. This particular one will be illustrated in part 11 of 11. Now part 10 will illustrate the two-stage nested design. And so, well, anyway, that's all I have for this. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.